record everything on the computer. Okay. You can remember the last time that even though that we didn't have a class yesterday, that we're going to have a class tomorrow. Okay, the office hours I'm going to keep tomorrow. So we had this discussion. Broadly, we had a discussion. The main part was that we were explaining that variation. These are we did so many times, many times. Okay. So mainly our focus when you have a like a see explanatory variable, see this x variable being quantitative. If it is quantitative, what are you going to get? What kind of a display we're going to see here? See, look at the scatter plot. And then we were, see, we were thinking about see, connecting these one. Can we do that like that? Yes, but at the primary stage, we don't do. We don't do. Okay, primary stage, we don't do. The reason is that that's called the splining, spline regression. That's called the splining. If you want to do like that, that's called the spline. The that may be that when it comes to and then oh, this is something. What is this? Okay. Connect. Close and connect. Okay, no, not this one. Okay, that's I did some calculation for the relative speed. Okay, not this one. Okay, then let's see. So what I'm trying to say that when you have this the third model, this the third model we are mainly talking about this model, regression model. Regression model X. Here you have height. Height is what? Quantitative. See, quant. This one thumb length Y. Y. Thumb. So also quantitative. See. Then you have the see some data like this. See. Then you get this line. Then you have a see X bar average of height. This one see Y bar average of thumb. Average of thumb. See. See. Average of thumb. See. Okay. So then we were thinking, can we connect like this, rather than this straight line? See, can we connect like this and get the answer, get the model? These are called the splines. So spline regression. We don't do that one at this class. Piece by piece, you're gonna connect 2 points at a time. When you do the advanced techniques, that I mean, like learn more, you can do that one. We don't do that one. And how about that? Are we doing something like different color? Say, can we do this one with like a curve? See, to fit in that one. See, it's called the polynomial regression. You're gonna talk about polynomial regression down the road. Polynomial regression. See, polynomial regression. Are we doing that one? No. Then what are you gonna do? We're gonna say at the primary stage we don't do this one either at we're gonna do the one that we are doing right now, but linear regression. See, linear, you are using a straight line to explain that. That's the linear regression. See, linear regression. See? Linear regression we do. So it might have about a simple linear regression, simple or multiple. Multiple. Okay. I'm going to use this one, linear regression, LR, linear regression or multiple linear regression, LR. When you have the simple linear regression, when there's only one X, there is only one X bar, X variable. When there are more than one X bars, we're going to call the multiple linear regression. So in our class, we're going to do this one. See, later on you systematically that you will be exposed to all these techniques, but you don't have to worry about that one. We have a heavy tool. We have a programming tools because we are dealing with a huge, massive data set. We don't do anything by hand. But I really want to mention that I'm doing this one all the time. Since you are trying to be, I want to bring you something that since you guys want to be that elite. Something I will show again. To share that one with you guys because something that because you really want to be that. See, I gave like a talk yesterday that based on the decision tree is like I mentioned that several times. Decision tree will replace the regression. See, this is the part that I really always emphasize. Okay, because we in the National University that compared to yesterday, I gave a talk at a different university in Michigan. But compared to what they have developed the program, they don't even use the R, SAS, Python. They use in some courses. We do using in all courses. So you are very lucky to have that kind of background because I mentioned to them that don't let the student to use the packages like SPSS and Minitab. Because the problem is that when you go outside and looking for a job, you cannot compete with corporation companies. They don't use the packages. They use the programming languages. SAS they used to use. I think they are systematically dropping SAS as well right now. They are doing pretty much everything in R and Python. See, this is the reason. In order to begin elite data scientists, I expect you to be full expert in analytics and statistics. So this part you cannot drop. This is the base. This is the very concrete, solid foundation that you cannot drop. That's why I little bit do. It's not theory. Okay. It's not theory. It's not about the theory. It is that the background, you have to have a background. That's why I always do little bit in addition to that going through that this one, because if you drop that one and then we run that program and get the result, you don't know what exactly happened behind that one. Then later on you are in deep trouble because when you go and work in a place, you cannot explain to the layman. Layman means people have no clue. You have to explain them very thoroughly. When the people who has a knowledge, you don't have to explain thoroughly. They can grasp and digest easily. But you go and explain to the layman. Laymen are the people non-specialist. Plus, if you run a company, your clients, at the end of the day, that should be well explained what you have done and then explain to them. In for that one, you have to have a background on, as I am showing over here in both the directions. So this is how they differentiate from each other. See? This create the hypothesis, but the statistics will play give the answer from statistics. This create the question. Okay? I mentioned a little bit. I show you that in that you get what's going on over here. Especially you need this one too. Business analytical skill, computing and software engineering programming skill, mathematics and statistics. Okay. And then part business trends order. So the straddle between the business and IT world is between those two. Because some people think that which part we don't need either. No, you need this one. Those are we are using the data science mainly in the that business. Now they call the business analytics as well. Okay? Okay? I think I made a mistake here. Engineering double E. Like that. Okay? Mathematics, business, second one. See, the knowledge and skill you should have, statistics and machine learning, coding language such as R, Python. We're gonna call the SQL or SQL. Doesn't matter. Databases. My is the name of the daughter of the I think inventor of this one, if I'm right. That's the daughter's name. They put my SQL or this one. Visualization packages like a Tableau, dashboarding, big data platforms like a Hadoop and Spark. You should know all these at the end of the day. So these are very important too, because you need that visualization, that platforms, that big data platform. See, 6 steps of data analytic process. Understand the problem. Data pre-process. Pre-process means you're going to clean up everything. That unstructured data, you're going to make it structured. And then missing data. They are sometimes the units were not even good. They were messed up. They have some data have a very huge variations. Data analysis you do that not only enough. You have to have the validation too and make a report. See? There are inappropriate data types that need conversion. For example, a lot of features need to be converted into numeric ones so that the machine learning algorithm can process them. There are errors of missing value. Most of the attributes means variable. Okay, you know that attributes means variable. In business world, they call the attribute value that need normalization. There are some features have wide different values range, so the value should be converted into roughly the same scale. Means you have to standardize. You know how to standardize. We were talking about even last time, in order to get the correlation coefficient, we standardize data. X minus or Y minus Y bar divided by the standard deviation. There are also attribute values that need to be pre-grouped or transformed into more manageable, meaningful groups. So these are the main data analytical methods. This is the part we are working on right now. These two together actually. Predictive part you're going to learn later on. PDA, EDA, PDA. See, this is the key part. These are the data that actually you haven't seen the real data. Raw data, you know this one. There's a training and test data types. These are heavy. Sensor data type 1, type 2, left, right interval. Sensor data with fixed removal. Sensor data with random removal. Truncated data. Pool data. Group data. Repeated data. Messy data. Structured data. Unstructured data. Especially even a machine learning, when you're going to utilize that under these data frameworks, is heavy. Raw data, okay, you get the training means you get a part of the data split into 2 parts, like a data that in our example, let's say that our chance of admit data, that admission data, you split into 2 parts. R can do that one easily. Like a 30 to 70%, let's say 70% you're going to utilize training data, means like a build the model, regression model built up with this one. But you validate by this guy, test data at the end of the day. See, this is you do all thing at the end of the day. See, deep learning, supervised, unsupervised. Supervised learning is the regression. Regression is one of the supervised learning. All these come under the artificial intelligence. See, this is the key part why you are learning data analytics nowadays a little bit. See? You know this one. See, supervised learning. Supervised means in that regression, you have to be provided with the machine to be provided X variable as well as Y variable, both to be provided. I have to provide this guy as well as this guy, both at the same time. Then he built up the model. With the aid of the model, he made the prediction about the next person. We need this one for prediction. Next person. So that's called supervised. See, classification, regression, logistic regression. We are here. We're going to learn classification, logistic later on. K nearest neighbor, decision tree. As I said, that regression can be replaced by this one. Support vector machine. Unsupervised means you're going to give only X variable only. They built up output and the prediction both they're gonna explain. See, unsupervised learning, principal component analysis. See, principal component analysis you're gonna learn in heavily in that 420, 420, 430. Sorry, 620, 630. See, these are again. So we are here. See, regression. We just exposed to regression. That's why I'm showing you where you are heading at the end of the day. When you cannot do more elaborative design, you jump into random forest as well. You really need to know all these to become an elite. Not only that, they are background about the statistics as well, programming and aspect with everything. These are the frameworks that you are working on. So you are working on this one, classical framework. And random forest means that the decision tree means non-parametric. They don't have a distribution like the one that histogram, nothing. Okay, look at this framework. So if you fail to work in this framework, you cannot learn all these because we don't teach. You have. I'm just showing that we have the solution. We have frameworks. Whoever interested party, they can learn one day. See? And something is precision, and these are very important. Biased and precision. See, this is the most important one. Unbiased and precise. See? Estimators. We learn in estimators. We learn in estimators. They have to be unbiased and precise. See? These are the variable models you can see. Mathematical model, rule model, neural. So mathematical model is the one that if you want to write a model for this one, you write the mathematics. You write that y equals b naught plus b1x. Can you remember? That's a mathematical model. But when it comes to the decision tree, you use the, not like that. You use the rule model and you use the neural network. See, look at decision tree, very easy. You go to root and decide. See? Non-parametric supervised learning algorithm, which utilize both classification result tree or regression. Same thing that we are learning right now in detail later on. This is easier compared to this, but it utilized so many variables, exhaust all the variables. That's in a very huge space. That expensive, very expensive. Look at that example. I show you like a real thing. You go ahead and check. Is there a swell today? No, you don't serve. This is the decision. If yes, then you have to go to next attribute, wind. And then if it's wind, you're going to say low to no wind. Yes, you serve. High wind, again, you check the wind direction, see, offshore, onshore, offshore, see, like that. How to come to this conclusion. So when you do like that, you build up the model based on that one. Excuse me, based on that, you see, you don't have any equation the way that we are planning to do over here. Here, equation. You play with the equation. So this can be replaced down the road. But in order for that to go, you have to know that there's something that not that much that cannot be easily handled. That's why you move on to something easy one. So this one more mathematical, and then it's easy too, but it's more advantageous than the other one. There are pros and cons in both. But what I'm trying to say, but this one most of the time they're using now. The machine is using this one. Robo is using this one. Machine learning is using another one. They try to sell something, see, online. So when a machine go and check whether the person's age, see, youth, middle age, senior, then say whether student or not, the computer, they're trying to sell a computer, see. They're never going to sell that. They'll send that advertisement for this person because he's a student, he thinks he doesn't have money, see. Like that kind of a setup, you can set up how to do the split, see, credit rating, excellent, no. See, you're going to buy the computer, yes, based on, see, you're going to utilize all the factors. That's why machine is doing, like that in a bank, fraud detection, they're using that one. See, another example, see, they're going to put they're going to advertise some kind of a watch merchandise online. They see their interest 1 to 4, never do, they don't get 4 to 7, yes, check the salary, 7 to 10, so check the salary, another attribute, another variable, see? Low and high, see, an average. And low, they don't buy. See, high, they don't buy. The average, they think buy. Then age, less than 40. No, sorry. Yeah, greater than 40, less than 40. See, yes, no. See, salary again, lower than 50,000. See, you can take into account all the attributes. But the thing is, when you write the R program, there's R program. You don't do this by hand. Okay. The same like, see, how do you split? These are that algorithms you can learn down the road, but so anything. You can split like this way. And the age even you can split, see, 3 ways or 2 ways. Binary or split multiple ways. See? Either way, how that can be done is no binary attributes. Even still you can split like a binary. Look at the continuous one. See, fair. How much the fare for that ticket that is based on the Titanic that the data is not based. So that's how they're gonna use the entropy, Gini index, something like that. Utilize how to check the first one. See, another example. See, based on weather, parental availability, health, they can whether what they're gonna do at the end of the day. We might some people gonna go to cinema, some people shopping, some people go for movie, tennis, like that. See, I did this one by hand, and eventually you check that. Whatever that attribute, the top one gonna get to the top, see, to here. From that one, now you're gonna check sunny day. How would be the gain? Score the information gain. Check. We don't do by hand. And keep going. See? At the end of the day, they decide, okay, yes, no, cinema. See? No, going to movies or not. See? No means go to tennis. So that kind of thing. This is that Titanic data that they're gonna see that it's somebody gonna survive based on not regression, but we're gonna fit in regression based on decision tree. Titanic data, see this original data. On board there were 1,300 or no 2,224, but we have a raw data or information only for the 1,309. Later on, see these are some information, some attributes, see survival, passenger class, gender, age, see siblings, see also see parent, ticket, fare, like that. It's the kind of a thing. See? Later on, we're gonna see add more to that one. We add more variables to that one, and then this is done by the R. See? Dictionary see? Advantages. No data preparation required, easy to interpret, more flexible. See? Here, overfitting. No, especially here that we fit this one is a several way. First, I put the only gender only. See, this is a simple linear regression. As I said, only actually this is a group regression. The group regression. This one, see, group model. This one, see, combination, combo, so multiple, another one, and all put together, and then come back and rest with the train data and test data. See, but unfortunately, the gap between these two is very low. See, going down. See, going down. See, going down is no good. It's called the overfitting, especially this one. See, you should even have one. That is a phenomena that the model has a higher prediction accuracy on the trained data set and subsequent drop prediction accuracy on the unseen data. Heavily drop. Like that. But what I'm trying to say that even though that we learn this kind of mechanism, this kind of a thing in the very beginning that can be replaced with the other machine learning techniques. Okay. So anyhow that see, as I said earlier, we have even R codes for that one. See, R codes. I have see Titanic and R code. I open that one along with the homework. See, it's a Titanic one. See, you can split. See, as I said, data can be split in several ways. 70% of data set as training set and 30% as test data. Okay? You can train one test like that. See? You use several packages, libraries. It's different ways you can do that one. Using the deployer, you can do that one. Using this. See, later on that data, same way that we see my data location, I put somewhere. See, train data. See? And then combine together. See, I'm gonna do different way to get the train data and test data and then combine. See, data combine, bind, rows, train and test. and you get it, you check it, and then you're gonna save back to your folder. See, this is how you're gonna save. Okay, if you want to save something, this is how you're gonna save back to your folder with a different name. This is the name being given here, data combined. If you want to give a different name, I'm gonna call that one now data, and save back to my folder. See, it's called write. Read means you're gonna read data. See, that's what we do all the time. See, read CSV. It's a write CSV. You're gonna read back to that one. Then I'm gonna read again. See, from there. See, then head and glimpse. See, glimpse will give you. See, right there. See, missing data. How to tackle that one? Those things you will learn. But see, later on, see, you're gonna mainly that when it comes to, I'm gonna show you that model a little bit. Same like the we use the regression. See? The R will do everything, so we don't have to worry about it. See, model 3, see, model 1. Let me show you. Model 1. Model 1. See? R part. That's the one that it. See? No, this is. Okay, keep going. No. Data frame. Still co-predictor decision tree with. I don't see. Yeah, model 1 is it? The simplest decision tree with the basic predictor, which is here. Same thing, survive. Survive is the Y variable. Then the data, I'm going to use not the data, whole data, train data only. Like a regression, same like a regression. We use the LM. Here they use R part, all that the decision tree. Same thing. If you want to use the linear regression, you put the LM. We're gonna run that. That's why I say that that's the we're gonna run that. That's why I say that that's the repeat other format. See, R part. We don't have to do by hand the way that I show that I had a 2 example, one by manually, one by that R. But we using R, we can get it done. See, you can put a LM here. See? LM here. It's not hard. See, later on I added more variable. See, yeah, some do the confusion matrix and all kind of stuff. But see, vision tree with the co-predictor. I added more. See, P class has cabin number. I created this one by looking at the number. Deck, fare, PP, train date. Right. Okay. But anyhow, that this is the beginning of that whole thing, whole discussion. Okay, it's the beginning. Okay, that's why over here talk about it. And the other interesting thing that when it comes to that this regression equation, how could you do? You know, let's say that this equation, this the equation of this. Sorry, last time we got that one too. I'm gonna say this equation. This is an equation. See, what is the equation? See, y hat equals b naught plus b1 x. See, b1 x. What is this? The gap between y naught, y hat means that anything on the line, estimated value. Let's say you pick a value, and this gap is what? Error. That's the error. The gap is the error. But the equation of the model, see, equation of the model, see, then you can say your data equals model plus other stuff. So the data is your thumb length. See, thumb equals what? Model would be what? B naught plus B1 height plus error. Look at the B naught plus B1. We're going to write again B naught B1 in another form. Y easy. This part we're going to call y hat, estimated y. See, estimated thumb length. Estimated We can simply say that equation of this fitted line, the same thing. Equation, okay, I'm gonna use this abbreviation for equation. Easy. See, fitted line, same thing. But x quantitative, y quantitative. Then where we can say something very interesting. How could we know that this the real B naught and B1? Look at the B naught. The B1 is what? B1 is the slope. Slope is nothing but what? Rise over run. You can remember. See? Rise over run. It's a straight line. If you go to the other side, you know rise over run. You know a straight line you can write with the aid of, in mathematics, with the aid of 2 points. You need only 2 points. Rise over run is the slope. 2 points. But unfortunately, that's not the case for statistics. Statistics need all the points to be taken into account because the points are not on the line. Doesn't matter. Some points are not on the line. Some point may be on the line. We got something best fit gonna go through this one in such a way that your sum of squared error is minimum. Okay. So when you get that one, sum of squared error, minimizing the sum of squared error, you got that line by creating a certain slope, rise over run. But even though I'm trying to write this one on this straight line in mathematical line, I'm taking into account all these points. That's the interesting part. In mathematics, you don't have to do. That's why they think your rise over run should be like this. It's summation of what and what? Summation of whose summation? X minus x bar times y minus y bar. You're going to get this product and then sum them. And divided by, we're not going to do anything by hand. We don't do, I'm just showing. See, that's the formula. That's B naught. B1. How about the B naught? B naught is nothing but intercept. Intercept. See? Intercept. See? That's the intercept. That's the intercept. That's the intercept. Intercept is what they give by the formula y bar minus b1 x bar. You don't do anything by hand. You don't have to do anything by hand. Okay? You don't do anything by hand. Okay? Then b1 that's slope positive. You're gonna say that's inclined to think. But in R you can easily get this one by running LM. See, in R we get this one. See, in R we get this one easily. But how? We're gonna say regression model. Regression model being given by LM. Here the height and your data. Height and data. Height and data. Then you have a B0 and B1. They're gonna display the B0 and B1. See, let's say that this one, if you as an example, let's say this one. See, I say tiny fingers model. That model, regression model. You have LM, sum, and height and data. Tiny fingers. Tiny fingers. And they call the coefficient. Okay? Coefficient means regression coefficient. Okay? Regression, okay? Regression coefficient. That means you get the first one is intercept, which is B naught. You might get 3.1611, something, okay? Height B1.9840. Then you can put it back. See, y hat is nothing but B naught plus B1 only. B naught is negative 3.1611 plus 0.9848 x negative 3.1611 plus for the given person height. If you know the height of given person, you can get the thumb estimated thumb length. Why we need that one? Because if another person gonna get into this one, we can easily figure out thumb length. Okay? Easily figure out thumb length. Let's say that if you put this one into this setting, x height, okay, that's a quantitative variable, okay, and here thumb length y, okay, okay, that's a quantitative too. Okay. So we saw that the way that negative value for this one and positive slope, see, look like this one. See? This length is how much? This length is nothing but B naught negative 3.1611. See? See? That's the see? Then this equation is what? Y hat B naught is negative 3.1611 plus 0.9848x. Okay. So, okay, looks like that. So let's say that our range, data range, gonna go from where to where? In thumb length, small thumb length. I think it's gonna go from there should be some height to some height. See, like this. Let's check a little bit real quick. What are the heights they taken into account? Let me see what are the height. See, let's say 62 to 70. I can get from the other side. 62 to see, height 62 to 71. No, I'm sorry. That's not right. Keep going. Where is the data set? Where is the data set? No. Okay, let's go slowly. Yeah, here. The lowest one 62. The highest one 71. 62 to I'm gonna 71. Okay. So you have a 62, 71. 62, 56. Okay. 62, 62, 56. Okay. 62, 62. There's a certain length. 62, the value is, I'm going to mark down. Okay, and show you. Mark down and show you. The thumb length is when 62, 56 thumb length. When 71, 68. Yeah, in between. See? Like that. See? Like that. Not this 62. There's no such 62. There's no such thing. Okay. There's no such thing. So our range here, see, our range here. Anything in this range, what are the other values? Okay, let's locate other values a little bit. Okay, I'm going to locate other values for you to see something. Other values for height. Okay, mainly height. Okay, not for the thumb length one. I'm not that one. Sorry, the height, not thumb length. Okay, let's say what's the next one? 63. If there's another point, 63. There's another point. Height 66, 67, 66. 67, 67. This one also, I'm gonna get that one out. 66, 67. The other one, 68, 62, 63, 66, 67, 68, 68, 68. Those are the heights. 71 also height. 6 heights. 62 is in height. 63 is in height. See, these are heights. So let's say that if you want 63, what is the value of this guy? And 62. I think this one, I'm sorry, okay. This is not the this line. This is not the, I didn't put to write this. It should be like this, not on the line. That's the problem, not on the line. Okay. Keep this one. This is estimate on the delete this one for time being. The estimated value, I'm gonna check. The estimated value should be from that one. Okay, sorry about that one. So in when 62, what is the value for this one? We can check that one. 62 value they haven't given here. So they go to, why I don't see there. No, the estimated value. Let me check the estimated value on the textbook. No, estimated value we have to calculate and get it. Calculate means running now, okay? Running now, it's not there. Okay, but their true value. See, these values, I'm talking about these values on this one, this one, this one, and this one, and this one. See, this one. So those are, if you want these ones, how do you get those values? You can get the predict. Can you remember predict? Now predict, and then you give the model. Model name is what? We call that one tiny fingers model. See? Tiny fingers model. Fingers model will give you those values. See? All the values on this line. See? Those 6 values can be taken by predict. Let's say that that one, I'm gonna call that one. Inside you do the intrapolation. That's called the intrapolation. See, it's called the intrapolation. See, intrapolation. That's the interpolation. Okay, intra inside. See, you estimate the value inside interpolation. Let's say in addition to, I'm interested in another one. Okay, another height. Let's say that I'm interested in height 61. When height 61, 61 height. There's something not in the data. How could I'm gonna get this one? Can I get this value? Can I get this value? This value? In order to get that one, what are you gonna do? You're gonna create something called the make fun. That's what I want to emphasize over here. See, if you need that one, you cannot use the predict. Predict won't give you, okay, because it's not a part of that original data. So you make fun of that model first. We're gonna call the height fun. Okay, I'm gonna make since I need this one, I'm gonna bring this one here. I'm gonna say height fun. See, height dot fun. Simple letter fun. Nothing but make fun. See, make fun is the function. Make fun of what? That particular model. Let's say the tiny fingers model or anything. height model, doesn't matter. Height, since I use that tiny fingers model. Whatever the name you have given, see. Use that one. Then you're gonna do what? Then you go to the height font, height dot font, and then put the 61 over here. See, 61 here. If you need that one. Don't use the predict. You cannot use the predict. You cannot use the predict. 61. Okay. 61 you put because it's not a part of your original X values. That's the difference why you are using a make fun and sometimes why you are using the predict. You saw why we predict. Anything you do inside, you call the interpolation. Can you do the extrapolation? Can you do the extrapolation? See? Extrapolation outside range. It's called extrapolation. If you do outside, extrapolation, that one. See? This is outside range, outside that one. Anyway, okay, let's keep going. Extrapolation on this side and the other side, okay. Extrapolation. You don't have to do by hand anything. You put that one, you get the value on this one. Then you have a true value. True value is that correspond to this 62. True value of the thumb length is how much? True value of thumb length is, let's go ahead and have a look at it. The true value, that's the value that should be over there. Okay. The true value should be correspond to 62. True value should be 56. See? True value, true thumb value, which is y, when height of x equals to how much? 62 is how much? Is the important thing they don't put very clear. The data is the key part. Thumb length is 56. 56. That is y equals 56. Okay. Y equals 56. Y hat is, how do you get the y hat? By predict. By predict. Predict tiny fingers data. Fingers model. See? You got that one from that one. See? Model. Then you take the difference between these two. Y minus, that's called the error. That's the error for that particular value. So they're going to do that one for each one. So you can find the error like that. Or if you need the error, this error even can be invoked by what? By the receipt function. See, receipt. You go to receipt and put the tiny finger. They will give you that one too. Not only for this one, for the whole thing. All points. For everywhere, whatever that difference between the y value and this predicted value, mean that value is the same values projection, that gap they're gonna give you. Maybe above or below, doesn't matter. True value below this one or above, doesn't matter. Okay. Receipt means residual. Okay. That's another way to get that one. You go this way and this way and this one. Do this way. And the same way, if you get the error, and then for this particular thing, if you go further down a little bit, okay, further down a little bit in addition to this one, if you get, see, x is nothing but height, see, y is thumb length, see, and then we have the points, 6 points somewhere, and we have this line, doesn't matter. Okay. So then Let's say we have x bar, whatever the value, we can find x bar, we can find the y bar average, and there's another line going through this one. See, look at that one, another line. And this is my point. I'm going to little bit up this one. Okay, I'm going to lift this up a little bit for my convenience, for to visualize it, on the purpose for the visualize. Let's say that my point is here. See, my point is here. So this gap and this gap and this gap, there are three gaps. See, my point, this is my true point. It's not neither on this one nor on this one. See, that's another issue. And then my model is here. This is my y hat. This is my y. Y represent any true value. Okay, this is my y. This is my y hat. Look at, this is my y bar. My true value is far away from y hat and y bar. Then we have to tell that this line is useful or not by looking at what? By measuring their error. Error is not a good measurement, because the error, when you're going to sum them up, you have to do the same thing for the other point too. This point, this point, this point, and this point. All the points you have to do the error. Error means I'm talking about the thumb length for a given height. When you do that one and sum them up, that creates a very huge problem. Zero. They add to zero. That's why you're going to square them. So this error, and the square, that one we're going to call the sum of square total. Total means square with respect to this guy. SST. This will represent all the points. Okay, that's why I don't have to draw this one for each and every one and then make this picture messy. So it's easy. I'm going to represent this one, all the points. See, this y represent all the points. Thumb length. What are the thumb lengths you have? That 56, 60, 61, 63, 64, 68, all the thumb length they represent for a given x. This one, that for the given x, height, isn't. So then this one is what? This one did not explain that much. See, still it cannot explain. See, this error carried from the empty model. See, empty model with respect to empty model, with respect to this one, being explained by this much, but still left over again this much. That this is the error due to what? Regression. Error not explained by my regression line. This is the error explained by my regression line. This is the error carried from the empty model. See, carried from empty model. It's called sum of square total. See, this error. This one, see. This error, see. Error, unexplained error from the empty model. Empty model. Sorry. Unexplained error from the empty model. That one. It has a name. Sum of square total. This one. See, this one. Okay. Unexplained error. From the regression model. Regression model. It has a name, sum of squared error, SSE. That. And we have another model. See, another one. See, sorry, another model, another one. See, explain error. That one explain error by the regression model. That's the error regression model explained. That one I'm going to call sum of square regression, SSR. SSR. See? SSR. See? So SSR, see? So see, SSR, sorry, SS total is nothing but SSR plus the SSE. This will be displayed in what? This one displayed in ANOVA table, along with what? Degrees of freedom. See, degrees of freedom of total is always n minus 1. Again, sample size. I'm going to make it clear, size minus 1. The degrees of freedom of total, this one degrees of freedom of regression. Regression is what? Number of x variable, x bars, in our case 1. Okay. In this case, tiny finger 6 minus 1, which is 5, this one. And the degrees of freedom of error is n minus 2, which means sample size minus number of parameters. I'm going to call them B0 and B1. Yeah. Therefore, 6 minus 2, which is 4. Okay. They also have a connection. See, they have a connection. They've been outlined here. Okay. Then degrees of freedom of total should be same as degrees of freedom of regression plus degrees of freedom of error. Okay. If you go to this one, degrees of freedom of total, how do you write it? Total is summation y minus y bar squared. See, this one summation y bar y minus y hat minus y bar. This one is what? Y minus y hat. See, look at, they were connected too, right there. So if you get here, you go further down here, this one, if you do mean squared there, see, mean squared total, it's nothing but, okay, on this side, mean squared total is sum of squared error, sum of squared total divided by degrees of freedom of total. See, on this side, mean square regression is what? Means sum of square regression divided by degrees of freedom of regression. Plus, I'm not going to put plus here, okay? I put the comma. I put comma. So they don't add to each other. Okay. Mean squared error is nothing but sum of squared error divided by degrees of freedom of. You go further down this one. This is nothing but whose variance? Variance of what? Y. That's another way we can call the var of thumb length. Okay? Var of thumb length. You go further down a little bit this one. I'm gonna get the square root on mean square total. That one I can call root mean square total. See? Root mean square total. That's nothing but standard deviation of y. Standard deviation of thumb length. See? It's the same. Those are all displayed in Word. So this one too. I'm gonna write to this side too. Okay. This means mean square total. This means root mean square total. That's what I want to say. All are in what? It's all are in what? ANOVA table. ANOVA table. All are displayed in ANOVA table. Then you don't have to worry about anything. How do you get that one? By how do you get this one in R? Go to ANOVA. You're gonna put what? Tiny fingers. Okay, that's the name I used. Okay, sometimes textbook use the different name. It doesn't matter. Oh, supernova. Supernova. Tiny fingers. Not more. Tiny. Okay, this one tiny fingers. Okay, that's the way you're gonna get this one. Whatever. Then we have to talk about simple thing that the correlation between those two variables. That's it. And then correlation. That correlation means like that. See how strongly they are related. See, X. This one is height. This is Y. See how they are related. See? Strength of their relationship. See? Strength of and Y and height. Strength of relationship between. Okay, I'm gonna write this abbreviation for between and height. 6 given by what? Given by square root of R squared. You know what R squared means? That means coefficient of determination. That's another name. Free. Can you remember? Free. Quotient of reduction in error. He did that one. Okay? It's the same name. Okay? How do you get that one? How do you get that this correlation? You can get the correlation in several ways. See? You can get the correlation in several ways. No, we discussed that the other time. See, correlation. How do you get that? Anyways, you can use what to get this one. See, thumb length is which is R. Sometimes we're gonna simple R2. Use a simple R, which is called coefficient of correlation. Correlation. See? Correlation. See? How do you get that one? You can use what? The code. No, you can use, see, as we that we have in this exam homework that we're gonna go to real quick today. Okay, we mentioned about the other time. See, co, see, right thing, co function, whatever that co, see, co of I'm gonna say thumb. Okay, I write it down. Okay, I write it down. You can see thumb height and data, tiny fingers. That's the one way to get it. Co, or you can use what? Co test. Co dot test. Test of, see, co test. Use the co test. Mainly that those three methods I'm gonna write over here. Co test, which is thumb. This one height and data. Tiny fingers. The other method I'm gonna get to the other side. Okay. So that one, what are you gonna do? You're gonna get the thumb. Thumb you're gonna convert into Z. Okay. How do you convert into Z? You convert into Z means you standardize. Okay. You're gonna standardize. Okay. Then you can say thumb, Z thumb. Oh, I'd like to say Z thumb. How do you get the Z thumb? You can say Z score or C score thumb. You go to data. I'm sorry, tiny fingers. Tiny fingers is the data name. Dollar sign. You can go to thumb. See, the other one I'm gonna say is Z height. Z height. Z score of tiny fingers. To tiny fingers data, then dollar sign and height. See? See? Then I can say the model. The model name Z tiny fingers model. Tiny fingers dot model means I'm gonna fit Z values. See, Z thumb versus Z height. See? You have put it back into that one. Okay, you have put it this back into your data, and your data tiny fingers. Okay. See? In this one, and when you run Z tiny fingers model, they will display B0 and B1. Okay, some value here. So B0 is the correlation. B0 is R. Okay. Correlation coefficient. Okay. That's all. Simple R. Okay. That's another way to get it. In addition to we mentioned about few other way to get it. And their strength in their range. We talk about their range, you know. Can you remember this? So I can remember in another day. We talk about that range in the very beginning. I can bring this back again a little bit for you to refresh your memory. The range should be somewhere. Yeah. See, that's the range. This is 65, 65. See, this one. This one. Let's see. Is there any way I can? This one. See? Oh, I can get the whole thing. Let me see. Copy. Did you go through? Okay. Can I paste here? No, it didn't copy it. 65. Okay. Oh, you can try different way. Okay. Um, so, copy and try to see we can paste it. No, it doesn't work, but anyhow that you know that is the ranges. Okay, ranges. Okay, this one. Yeah, yes, it. If the range R or capital R doesn't matter, it should be between minus and 1. -1 to -0.7, -0.3 to 0.3. There's no relationship at all, no correlation. Here to here, included, excluded, this point, included. Here, excluded, excluded. See, both. That third range is no correlation. First one strongly negatively correlated. -1 is perfectly negatively correlated. That means the higher the value of x, lower the value of y. Perfectly. The other way around. Slant to this one, straight line to this side. Okay. The negative means this side, the slope. This side. So see, this not included, this not included. This point has been taken care of. It means perfectly negatively correlated. Then within this range, excluded, excluded. That means -1 to -0.7, excluding endpoints. That range, we can say strongly negatively correlated. The two variables. Included, excluded. A left endpoint included, right endpoint excluded. That range 0.7 to -0.7 to -0.3, mildly negatively correlated. Included, included. Both endpoints are included, -0.3 to 0.3. No correlation at all. If you see that kind of a value, no correlation. Write something like that. This one to this one. Excluded, left endpoint, excluded, included. So the fourth one, that positively, sorry, this one means positively correlated, mildly positively. Within this range, exclusion and exclusion, they both excluded endpoints. 0.7 to 1, strongly positively correlated. The last one, positively, perfectly positively correlated. So when you have a negative side, that means when it's negative, that the line always slant. See, I mean like that. See, not like this, like that. Okay. So here, see. So let's say that I'm gonna just virtual. This one, see, if you have something like this, see, that's a negative. See, negatively correlated. Negatively correlated. This one is the line is slant to positive side of x, positively correlated. That's the idea. It's kind of like a rough idea. Okay. You can get this one. So that's the whole discussion they built up over here in this whole chapter. Okay. The whole chapter is all about that one. We saw that one. Okay. Then we can move on to that the major discussion, that homework. These are, we can. Residual, we talk about that one from the residual, different ways we can get this done. And I want to show you a little bit one more thing. Okay, one more thing before we move on to homework and finish it up. This one, as we do all the time, there are two versions of this whole discussion. Okay. So, whole discussion. The whole discussion, sample version. This one. Sample version. This one sample version. Okay, that's okay. Normally take to the side population version. I'm going to take the population version. Population. I'm going to write population with this abbreviation. POPO superscript n underscore. On the other side, we can say the sample version. Sample version. The sample version is the one that we are dealing with right now. Okay. The sample version you have here y based on the data. See this one. Now height is this kind of a line and y hat. See y hat. Look at. I'm gonna write y hat b naught plus b1x. Okay. And the model I'm gonna write data equals model plus other stuff. I'm gonna write y equals b naught, you know b naught, b1x plus data. This part is y hat. See? Y hat is nothing but y equals y hat plus another way to look at it. So counterpart, we think, look at x is height. This is some length y. Okay, look at what's gonna happen. For a given one height, let's say we can remember 62, no? First one, all the way up to 71. They think, okay, for this one, they think that for a given height, there are infinitely data points, okay? Infinitely many data points. That's what the theory thinks. Okay. Come on. See, for this one, we normally have only one dot correspond to that one. Let's say that correspond to this one. See, this is 62 in sample version. See, only there's only 1 point. See, one data point. But here they think, see, infinitely many. See, okay. That's why they think you can draw a smooth histogram and get the smooth curve scheme in that one. See, like that. So see, histogram. You can draw histogram. Then I'm gonna, rather than go to that whole data, I'm gonna go to the center. You can remember we had that discussion. Center would be a best single number to explain the whole thing. I'm gonna denote this by mu. See, center mu. Center mu. See, mu. Can I do the same thing for this guy? Yes. See, for this one also they believe there's a infinitely many numbers. For my convenience, I'm gonna draw to this side. Okay, histogram. See, again they have something like this. Okay, interesting. Another distribution. It has a mean too. See, it has a mean too. See, this is the mean. Is another mean. It also mu. See, are they the same? No. Are they the same? No. Different mu. But I put the mu for that one to represent that one. Okay. What they gonna do? They go to all the points and draw a line which gonna go through that one. See, for the means. See, means. So your equation of this one is nothing but mu plus the intercept plus slope times the height. See, you know that one. See, height. Who's mu? Mu is nothing but we're gonna say in mu another name expected value of height, thumb length. See? Expected value of thumb length is nothing but we don't say average in population setting. We say expected value. The population mean. This one actually population mean. See, population mean. Population mean. How are we gonna say expected value of thumb length is nothing but sorry, intercept. This one, intercept plus slope times height. That's why equation is like this. the E of Y, the expected value of a thumb length. Oh, mu equals beta naught plus beta 1 makes, see, look at how they did. EY, you can say EY, expected value, or mu, beta naught, beta 1. See, that part, see, EY, only. I'm talking about same way here, see, this part, see, we wrote this part, see, like this. Later on, if you write the model here, see, your data, if you write the data, your model plus other stuff. The data is Y. See, Y. Model is what? Beta naught plus beta 1 x plus epsilon error. We mentioned that one. Epsilon. Okay. So this part is what? Not Y hat. This part is nothing but expected value of Y. Expected value of Y. What do you mean by expected? If you do something in a long run, that's how people looking for that profit for a big corporation. In a long run, see, I'm talking about expected value of that part. That's nothing but the equation of that line which gonna go through the average of that one. See, here the same thing. The model is nothing but the equation of the line. Here the same thing. Model is nothing but the equation of the line. In sample version as well as in population version. Population version. Okay. Population version. See? Okay. That's why they were connected. So you have to learn the parameters. See? We can say same to this one. See, beta naught and B1 are parameters. They are named parameters. See? Cannot be calculated or evaluated or computed. Cannot? No, it cannot. But they can be estimated. See? Can estimate. Now, but the B naught and B1 are statistics. Their name is statistics. Can be calculated, evaluated, or computed based on the given data or with the aid of the given data. Therefore, you can say, see, therefore, see, look at the symbol for therefore, see, you're going to put like this. 3 dots at the vertices of that equal triangle. See, therefore symbol. Therefore, we can say B naught is an estimate of beta naught. B1 is an estimate of beta 1. E is an estimate of epsilon. You can tell like that. What kind of estimate? Now you might be thinking, even as in the slides you saw that, what kind of a estimate would be what? What kind of estimate that we can, you go to the which estimate? You can get the so many estimate based on the so many samples. Which estimate you're going to utilize? What is the best estimate? You go to the best estimate. Because we're going to learn about that one pretty soon. B naught. You don't have only one B naught. You can have a whole bunch of B naughts pretty soon. Next, that section next week we're gonna learn. It's not just a simply this one only. It's not simply this one only. It's not simply this one. You saw this can be fitted into the distribution. So many errors. This one too. How many errors fitting into this one? And then this cannot be repeated. These are repeated measurements. Repeated measurements. You have to do the repeated measurements. Yes, when you're gonna that let's say measure the length of a desk. One time you measure. Second time you measure. Third time you do this 1,000,000 times. Do you think you're gonna get the same value? No, they vary. That variation has to be addressed. That's what we are doing in data analytics and data science. Variation is the one that we take out all the time. Variation called the error another. Okay? So this an estimate. So what kind of estimate you are thinking about? When it comes to the estimate, okay? Estimate, you have a minimum variance. Some estimate will produce a minimum variance. I'm not talking about the variance of the thumb length. I'm talking about the estimate will create that, because as I said, you have a B naught. B naught has been taken, see, several times. See, B naught. Let's say, one time. B naught. Second time. Keep going. And then B naught. Let's say 1,000 times. See, look at 1,000 times. B naught repeated. See, like that. Then from these B naught, which B naught I'm going to pick into? Which B naught? They think that we have only one B naught based on. These are based on simulated data. You simulate. You don't have a data. You have only one data set in your hand. You have only one B naught. Even if that's the case, it's not fair for you to think that your data is the only data set that's gonna produce that right B naught for this given scenario. Think about someone else has done this one. He might gonna come up with a different B naught. That's what we have to make sure, that giving an opportunity for everybody, leave the space for that everyone to produce their own values and then take into account. That's very fair. I mean, that's the way models should be built up. You cannot just simply say, oh, I have a data. Who observed these data? Only one institute or one person or a group of persons. Or what happened to the rest of that groups, institute, and other people? If they're going to do that one, do we come up with the same values? No. That change, that variation to be addressed fairly. See, that's what we are doing in statistics. That's why statistics, if you used anywhere in any system, mainly that if you use that mainly in legal system, most of the time that some people that the culprit, they go home, or that innocent people incarcerated, that can be easily prevented. But unfortunately, that scientific reasoning and legal system, and they don't go together. They go parallel. They don't do think collaboration. They don't collaborate. They don't do. They don't do at all. That's why data science we cannot easily utilize in legal platforms. We use in that big corporation only to make the profit only for the purpose of making massively profit. That's it. But to bring that other kind of aspect to that, looking into that one, we can easily use when somebody being that let that person go home, or they're being convicted. Is this person is a real culprit? You come back and then check it. It's called the Bayesian theorem. Bayes theorem. You have to use it. We don't do that now. But what I'm trying, that's why this one we cannot use in that platform. Mainly we use in the like a big corporation to make money, and then with the aid of this, as I mentioned earlier, with the slides and machine learning nowadays. Okay. Anyhow, see, we leave that space for anybody to see. But can I use that whatever the value that in my hand as a base estimate? Yes, that's the tricky part again. Why we gonna let you to that use that one? If that's the case, why you go back and bring up this kind of a discussion? Yes, we have to bring up that kind of a discussion and say, hey, it would have been like this way. How would that be? But we don't have these values. You can simulate these ones. Even if it's simulated, you eventually come to that B naught. There's a one B naught here somewhere. Okay, let's say that to make it, I'm gonna keep going this one. Okay, and they say that B naught. There's the same thing can be applied to, I'm gonna call this one B naught observed, see, to make it more clear. See, this one, see, B naught, this one I can say observed, see? Observed. That's the one that we're gonna utilize. Can I utilize that one for my calculation? Yes. Would that be fair? Yes. There's a, because when you draw the histogram for, can I draw the histogram for this one? Yes. Can I draw histogram for this one? Yes. Look at this time what I'm gonna do. I'm gonna draw histogram for B naught. And then I'm gonna get the smooth curve. If I go to the center, interesting part is your B naught observed is would be the your center. That's the interesting part. See, in that sense, and I use my whatever the B naught one, only one data set you have. Can I do that one? Yes, see, because of this reason. Now you gonna expand then your the knowledge you had earlier. You were thinking, okay, I ran that one, I got B naught, that's enough. No, that's enough because it's going to be the center of the distribution of all the B naughts that we taken into account. Doing what? Either you running this one several times, or so many people running this one at several places and put together and then taken into account. See, it's going to be millions, billions, trillions, doesn't matter. Can we simulate this one? Yes, that simulation we're going to talk about next week. We generate, yeah, we generate that one. We generate. Then we engineering data. Those are called the engineered data, the generated data, simulated data. See, this all are, see, this all are, see, all the simulated, or generated, or engineered data based on, I'm going to say based on. Based on. Can do that one too. Try that. See? Then would that be a good, I'm talking about the B naught. Then which B naught I'm going to take as a this one. This one has, I'm going to call this one. Look at its variance. See? Variance. B naught has a variance. See? B naught has a variance. Which one we're going to pick? When you draw different group, different distribution for to scheme in the top of that one, some people might gonna draw a picture that is with the like a higher this length, which is the spread, which is the variance. Some people like this. Which one we gonna pick? The one with the not only center enough, you have to pick the one with the what? Minimum variance. See? Minimum variance. This is, if you pick this one, we're gonna call unbiased. See? Unbiased. That's true because you pick something from center or close to the center. See, not only that, you have to take into account the center as well as the spread. See, that's the center. And whose center? Center of B naught distribution. This one what? Spread of B naught distribution. Do we have to take into account this meaning standard deviation? That's a standard deviation or variance. Can you take into account the mean? Yes, mean and standard deviation, you really need to standardize something. Same way here. See? So because of that, if you put these two meters, put the pieces together, you're gonna say minimum variance. Uniformly, we're gonna say uniformly. Okay, uniformly minimum variance, unbiased estimator has been abbreviated as like an acronym UMVUE of data node It's B naught. And make it more specific, B naught observed value. Obs means like a based on the your given data. Okay, UMV. Can we do the same thing for B1? Yes, we do the similar in a similar fashion. You can do the same thing for B3. B1 also you can do that one. B1, the first one. B2, the second one. Sorry, B1, second one. Dot, 3 dots means continuation. Then I'm gonna go to the B1 based on the observed value. See, obs, comma, dot, dot, and B1, 1000 times. See? See? The similar way that you can talk about that one too. See, that one too. You can draw the histogram. One, you can talk about uniformly minimum variance unbiased estimate for that one too, which is the value that you used. In our case, that B naught would be what? B naught would be based on the value. Can you remember? We calculated that one. See, see this one. 3.1611. Negative 3.1611. Negative 3.1161. So that one is nothing but 3.1611. In a similar way, can I say the UMV of B1? Yes. UMV, uniform minimum variance unbiased estimate of data node is beta 1. I'm sorry, beta 1 is B1 obs, which is 0.9868. I think if I can remember. 0.9868. 0.9848. I'm sorry. 0.9848. 0.9848. That's how it works. It's same thing, same way like this B1 distribution. That's the histogram for that guy. Always the histogram playing a heavy role, okay? You don't have to draw anything by hand, okay? And if you go to the center, that's called the B1 ops value, which is 0.9848. That's fair for you to pick the center of the distribution of this one. See, this is the distribution of B1. Distribution of B1. More specifically, I'm going to go further down a little bit to that, I'm trying to lay down a foundation for next week. See, they are related, okay? Sampling distribution of B1. More specifically, if I say. Sampling distribution, because based on the sample. Various samples. Same way, see, if I go back to previous page and this one, I say the distribution of this one, I can say distribution of, sorry, distribution of this one, distribution of, see, distribution, I'm going to use this abbreviation for distribution. Distribution of B1 is more specifically, I would say sampling distribution of B1 because it's based on different samples. Different samples. How do you get this one? Based on one sample. How do you get this one? Different on second sample. How do you get this one? Based on my sample, my available sample. How do you get this one? Based on another 1000 samples. 1000 samples. It's nothing but you have a population. See? From population, see? B naught. Can I get the B naught one? Yes, see, based on what? Sample 1 of size n. What is the size? 6 over here. Can you remember? Can I get another one? B naught of second one? See? Yeah, that's the same second sample. Sample 2 of size n equals 6. Okay, keep going. Then do you have a sample, observed sample? I'm gonna say observed sample. Observed sample. Yes, that create what? B naught of, okay. That would be how much? -3.1161. And then keep going. This one. Let's say 1000 sample, okay? Sample 1000 sample of same size. Sample of this one also n equals size 6. Size n equals 6. You create that one, and can you calculate the 1001? Yes, we're gonna talk about that one next week. See, we don't know this value, okay? We don't know this value. We don't need that value. See, those are based on them. See, like that. That's how we got these values. We not drew the 1000. I drew the histogram from that one. That's the same way that you can do for the B1. B1, if you do the same thing for the B1, they calculate that. We're going to learn that one next week, but this is related to this week word. We cannot learn anything standalone because they are related. See, this one based on the same sample. Sample 1 of size n equals 6. Can you calculate B1? Oh, yeah. See? Then sample 2 of size n equals 6. B2, sorry, B1 of the second one, yes. This one, observed sample. That's a sample I am having in my hand of size n equals 6, which is B1 of nothing but 0.9848, no? And keep going. Sample 1000. Can you simulate? Yes, you can simulate. 1000 of same size n equals 6. B1 1000. Okay. Those are the one we utilize in order to draw the histogram. We can generate this value. We generate this one, we don't generate this one. It's already within the Venn sample. The rest we generate. It's somewhere standing somewhere among these values. That's what I'm trying to say. That's the kind of a discussion if we broaden that discussion, that's what we are planning to. We're gonna broaden our discussion, expand, okay? Because you know that I have to tell you something very clear. When you do bachelor's, you learn the stuff on the surface, okay? On the surface. You don't have to be ashamed that if you don't know that much of the knowledge or that much of material, because even some professor might gonna be harsh on you and then say, hey, you have to know. No, that's not the right way. You don't know because you touch that one surface, just very barely you touch. When you do masters, you're gonna broaden. You're gonna expand knowledge, broaden, expand. When you do PhD, you dig deeper. You go down and dig deep. So when you do postdoc, you go deeper and deeper. Then you go to the some faculty or researcher, you keep digging and expanding both every direction like that. So the knowledge at this stage, since you are a master student, we are digging now. Sorry, we are expanding knowledge. We're not digging. That's why we don't do too much. But you don't have to worry about, we don't know, because there's no endless, because the knowledge, there's so much thing to learn, we cannot do like that. But that up to you to explore more and more that everything behind this one and the codes and everything and how they relate to this one and how to connect to this our discussion right there. See, it's not like a merely just learning the codes. No, it doesn't work like that way. But I want you to be an elite data scientist at the end of the day. Okay. Let's quickly look at this one. Okay. Let's go ahead and look at our data set. Data set say admission data. Admission data to what? Admission data we are using. Let's look at the data set. No, 625. Assignment. Homework. This one. No, sorry. I was in the wrong. No, 605. Assignment. Homework. This one. See, this data variable you have seen already. This one, see, GRE score, TOEFL score. See. This one, okay. Cumulative GPA research, okay, research, chance of admit, like that. Okay. So see, these are variable. We're gonna see what is the chance of admit for the next person who will be taken into account. We're not gonna talk about this person again. I mean, these are based on that some people's information. That information we can utilize in order to predict someone else chance of admit to the university based on what we've taken into account to explain this one. Let's say chance of admit being explained through research. By looking at the research, before that, they're going to come and ask, okay, I have done research. Okay, then we're going to say, okay, you have a chance of this much of a point, not this much. Based on that, whatever the model we're going to get. This is for that particular person, first, whoever in that research, that his chance of admit is almost like a 0.92. Not only this one, because here this information they have collected. Based on that one, we can talk about by asking him whether you have done research or not. Yes. Your estimated value not going to be this one. Maybe your estimated value may be 0.85 estimated value. See, on average, we can say you have like a 85% chance to be admitted. See, 85% chance to be admitted based on that. That's what we are trying to build the model. Later on, you can say, how about based on the cumulative GPA, grade point average? How about based on the letter of recommendation? How about based on the statement of purpose? How about the university rating? How about the TOEFL score? These are for the, I think, the TOEFL score that you don't have. If you are an international student, you might have that one. But the local, the domestic student, they don't have this one. They don't have to take this one. But if you need the GRE score, you need in order to go to the grad school, graduate record exams. Some school, some program, the way that to propagate that one, they don't take into account GRE most of the time, regardless of you being international or domestic or local or regional. The most university, they require this one GRE. TOEFL, this one. So for the admission, university rating like that. With this data being produced by, I think, somebody. Let me see. Who did this one? Let me see. Let's see. The Mohan and Acharya, see. Couple of Indian people, that student with comparison of regression model for prediction of graduate admission, IEEE International Conference on Computation and Intelligence in Data Science 2019. Yeah, IEEE. So they were checking that chance of admit to research, then you can fill in this one. You can get R in different ways, easy, B, not. I mentioned about that one in the last time. We can have a look at it. So when you get this data, let's see. Data is the data. I got data, that's open. Data good, glimpse. Okay, I have to I cannot give the glimpse until that I install package Mosaic. Okay. And let's load it. This one. First one, research experience. As I said, you can record that one, go to the data and the research. Zero, I don't know whether that time worked last time. Yeah, this time worked because the last time, can you remember we had an issue? Because they messed up because sometimes that it's restart and then messed up. See? This time we didn't have that issue. See? You can do that one because last time I used this one only. You see, this one you can that replace because in order to rather than go by number, go with that string. In that way, we know clearly which one is no yes. Otherwise, we have to keep coming back and then check it. Zero. Sometimes the machine, you have to understand something too, that the machine will assign if they're gonna do, but you can remember when we using the entile, so sometimes they assign 0 for no and yes for one. Can they do other way around? 0 for yes and then 1 for no? No, they don't do. The reason is that they are doing everything in alphabetical order. See, N, letter N. You give the first number to that one, and then Y. You want like that. Anyhow, see, like that. See, so now it's been this one, or you can use the factor and get this down. It says the yes or no. See, I call with the two different one. They will be saved back to that data set. Okay. See, research factor one. See, research factor one. See, right there. Then you can graphically check that how that chance of admit. See, in faceted with respect to that research fact. I'm using the research factor. Yes, no, no. You can do the same thing. See, this one. Oxford. So this one. Then you can find the correlation. See, chance of admit. I'm gonna z-score. And now see, so z-score. Chance of admit. Let's wanna see head that. See, chance of admit here already. Z-score. See, doesn't come over here. I don't see that one being saved back to SOP, LOP, G, researcher son, admit, research factor. Can I put this back into data? That you see, put the data and put that one, and then go to data. See, put it back if you want a data, and this one put it back into data if you want. Save in the data research one. You're gonna convert. See, that it's the research. See, standardized research. Ah. Mm. Research not found. Let me see. This one. Yeah. This one, Z research. Okay, this one, Z research. Show. We have been converted and this one was C research. Oh, sorry. Head of, sorry. I know what happened here. I had to give the date. No, no, this one head of the cancer of admin. But when you go to the head, it shows this one. Why? It's a narrow down this one. Okay, I do like this. See what's going to happen. Yeah, now show. But this one, just so 31 mentioning data. If that's the case, mention about the data and then report. We have that issue over here. And then data. Okay, see research over here. This is here. And this one, let's say this one down. See. When I ran I fitted that see the standardized cancer of admit versus standardized research. Then I got the B1. Let me see this B1 works this time. No, doesn't work. Okay, I'm going to install Supernova. Supernova should have the. It works. Last time again. Last time is not in the class, but when I was running, it was working. That's why I put over here. Okay. Still have an issue. Could not find function. That's okay. But anyhow, when you run, see, V1 research correlation, V1 slope, that's the same thing. But here, this is the one I'm talking about. See? Oh, you can look at here. This one, okay? Research function, copy, research name underscore correlation. I'm gonna say this one. No, I need only this word. Correlation, I can say research, no, regression. Not the regression, sorry, not that one. I have to get, I had to run regression, okay? First I had to run regression. And then we can give a name for that one, okay? I'm gonna run this one here. No, not the regression. I'm gonna get hold them. Okay, that's okay. This is what I'm talking about, okay? I can say not the Z regression, regular regression name. So the name go by all the time with the research dot model. Okay. We call that research dot model. Nothing but LM chance of admit research data that no, you don't need this here something. I'm running that regression between original data set. Its name is research dot model. Model. This one. Then, yeah, that's the one. Okay, that's a different one. That one I'm trying to over here research dot model. See, research of model. Research of model. We don't need the data. It's already been set up with the Pearson. Pearson doesn't work. Right? If you put that just that name of this model, and the correlation doesn't work in that format. Doesn't work. The correlation method. Yes. Okay, let's take this out and see. Such correlation. I'm gonna go back to the here. On place. LM chance. Oh, can I erase this one? Hold on. Yeah, that one. I will know this. Sorry, this one. The third, this one. See, that one. No, see, doesn't work. That's why we are using the whole thing inside this one. Okay, that works. Research correlation. No, it came back to the same thing. I'm talking about this one. This one doesn't work. This one doesn't work. This one doesn't work. So we don't need this one as well. If you need the research correlation one shot, you have to put that inside the this format. Okay, that's the same answer like this one, not this one, not this one, this one. So you can use what? Code test. Code test. It's giving you t value, this one p value, see, alternate degrees of freedom, how many things? That's one give you that everything. Pretty much. See, and then this value, I'm gonna focus on this value. See, for several method we talk about. See, you can go to the see research this one, see research regression, or you can say research model. Doesn't matter. The same way that we had earlier. You run this one. See, another way to get this done. See, then go to supernova, run supernova. See, from that one you get the pre-value. You get the pre-value, as I said earlier, pre-value, get that one and find the square root on that one. That would give you the same thing. See, that's the same thing. Or you go to the regression model and run the pre doesn't run. If B naught doesn't run, this doesn't run. I have to check again. It's been running, something wrong. See, or you run the ANOVA table for the original variable. See, go to ANOVA table, you get these two, sum of squared. See, this one is B, sum of squared error and sum of squared research. Then you're gonna add and then addition. That simply I'm trying to say that this value divided by this value. That's what I'm trying to say. This value means nothing but sum of squared research in this case. See, sum of squared regression. See, go to the research. Go to the research in ANOVA table. Go to the sum square. See, same name you have to give that. This is the row. This is the column. That value they're gonna read. See, A is nothing but that one, 2.48332. See, same thing. It's reading it. And reading this value as well from B. See, you do the same thing. Find a see, then the total. See, this one. And see, P value. Then take the square root on that. Same thing. So similar way you do it for the everybody, because you have to fill in this table. We had that discussion the other time too. See, there's the number here. You have to fill in all this with respect to and CGPA, GRE, total. B naught. In this case, B naught is how much? B1 is how much? Let's say that B naught already we checked that B naught in that model. Set the model. Yeah, this model B naught 0.6377. But the B1 0.1583. I'm talking about this one, this one, this one is how much? Point, that R, we calculated R in so many ways. 0.5532 if you round to the 4 decimal places. 0.5532. B0, you know, B1, you know. Degrees of freedom, if you want, you can get for error. Okay, get for error. Degrees of freedom for error. See? And the SS model, degrees of freedom for error, go to over here, either this model or this one. Error is how much? Other error means this one, 398. And the other one, you know, you need the sum of squared, sum of squared for the model means regression, this one. Okay. That value is nothing but 2.483. And you need the pre-value, 3.3060. You know, you need the F value, 175. See? You can easily fill it. You do the same thing with the simple linear regression, one variable at a time. See, second one, see, this one, GRE score. See, this one you can say simple linear regression of chance of admit versus what is the other one? Research. See, so uniform. You see one x value. See, that's how we call simple linear regression. See? Versus that one. See? Simple linear regression of chance of admit versus research. So the similar fashion you can talk about, see, simple linear regression of chance of admit versus undergraduate GPA. Undergraduate GPA is, you can say, CGPA. Cumulative GPA, CGPA. For that one, even you can graphically see whatever you want to see. Simple linear regression. And the next one, see, you can say this is simple linear regression chance of admit versus GRE score. GRE is a GRE or GRE score. Okay, name GRE score. See, put the same name as it is. GRE scores. GRE score. See? Then you do the graphical representation. Next, the same way. One method enough for you to find that one for R. Okay. That's okay. And this one, TOEFL. Test of English as a foreign language. TOEFL or test of English as a second language. TOEFL or the TOEFL. Okay. Some people, foreign language or second language. See, you can get the values and fill in this everything very clearly. See, this everything clearly you can fill in. And then explanation you can put here. See, interpretation R. How do you say that research experience R? Let's say that research experience R is 0.5532. How do you explain? You can say those who have research experience coded have a higher chance of admit compared to those who do not have research experience. How much is the chance strength? 0.5 to 0.55. You don't simply say positive or negatively. You cannot say negatively or positively correlated. Look at by looking at our that ranges, it's going to be between what? 0.32, 33 to 0.30 to 0.70. It's mildly correlated. You cannot say that positively mildly correlated. They say don't write that kind of a thing over here because they explain in elaborate in plain English. They elaborate correlation between two one categorical and quantitative variable do not indicate the coefficient is positive or negative. Rather, use a description. Okay, the description is this one. The second one, between what and n, the expected or mean chance of admit for those who do not have a research experience, coded 0 is 0.6377. See, that's the B note in that one. B1, which is point, see, this one, the expected mean chance of admit for those who do not have a research. See, can you remember B not in group? This one group, no? Actually, to make it clear, I'm gonna come back again here. This one you can simple linear regression. Then I would like to say group. Okay, I would more elaborate. I write here simple linear regression. I would say group model. Make it group model. Group model. The second one, because it's categorical, then this is second thing. Your regressive variable categorical. Okay, same way little bit. Let's go to sorry, see on the second one. Where's the second one? Model 1, model 2. See this one. See, you can say again. No, not the group model. This one regression model. Regression model. Regression model. Because see, chance of admit quantitative, CGPA quantitative. Regression model. How about the next one? That done. Then GR is go again. See, regression model. Third model. Models. Then this one TOEFL score again. Regression model. No, see. So regression model. These all are regression, group model. But you can get the value this quantitative to quantitative. Quantitative B naught and B1. How do you explain? See? Okay, this one. See? Okay, this one go. Then GRE score. Look at the GRE. Higher GPA scores are associated with the higher chance of admit because of positive. What is the value of that one? What's the value of this one? High chance of admit with correlation. So you can run anything. See, chance of admit versus GRE score. I'm looking for second one, CGPA. Okay, this one, CGPA. Okay, how to get this one? Let's run all these. That's the same thing. No, could not find B. Oh, okay, I don't need the B1. Let's stop over here. Yeah, here, I got that one. See, 0.8733. See, 0.8733. So that's the same thing we can find from here. See? 0.8733. So this one in the description point. Hmm. 8733. 33, that's why they say that if you have the two quantitative variables, what are you going to do? You're supposed to say something like this. When B1 when B category explanatory variable, quantitative explanatory variable, B1 quantitative explanatory variable describe whether the outcome variable is expected to increase or decrease and by how much for each until each unit change in the explanatory. By how much? See, each unit change in higher the GPA. How much that if you change that if your GPA change by 1 unit, how much is the chance of being go up? See, sorry, not I'm looking at the R. When you take those who are in, then you can say if it is a quantitative, do not indicate positive. A greater distance from the associate, more current. Yeah, you can say the higher the GPA score, the higher the chance of admit to the that school. See? The higher the GPA score, the higher the chance of admit. Okay? D naught is what? The expected chance of admit for someone with the GRE score is 0. The GRE score, what is the chance of admit? Negative value. We can tackle that one. Then B1 is what? For a 1 unit increase in the GRE score. Sorry, looking at the wrong case. Of the GRE, where's the CGPA? CGPA, even the GR is the same thing. So, this so this one. See, they cannot scroll. Okay, this one, that's the first one. Okay, what is this one? See, keep this versus research. CGP, CGP. Yeah, see, yeah, information here, CGP. Second, CR is possible. 1 unit in GR is called student expected chance. See? Students expected chance. See? Increase by how much? This one. The proportion of variation in student chance of admit explained by their GR score. See, the proportion of variation in student chance. You don't say simply that proportion of error means error. See, rather than that, they say to explain this and the proportion of variation in students' chance of admit explained by GR score is this much. You see, they can explain this much. Their chance of admit. Same way here, the proportion of variation in student chance of admit explained by the whether they have a research experience or not is this much. Same way that if you keep going that GRE score, GPA, where's the GPA one? Don't have a GPA. Yeah, you in a similar fashion, you have to put that one for GPA, TOEFL. No, I haven't written that one. Same way you can write it this down. Okay. The same way, I put the same dot 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 continuation. Okay. See? So you can do for the research experience. Then you can do for this. The other one for undergraduate CGPA. Same way you can write it down. And the later on you can write it down even for the what? See? TOEFL scores. Can do the same. Now they're gonna ask about them. See the explanation. Oh, explanation you don't need that one. No, for the everything. I think for the homework you don't need. You need only for the two of them. That's okay, but for your own convenience, that since we have looking into these three homework, which model is the best model because the PRE, which one has the highest PRE, look for that one and see. And then which model is according to F ratio, same highest one, see. You can say highest PRE, the model with the highest PRE. Model is the highest PRE. This one you can say the model with okay, highest F And this one, obtain prediction for the following prediction, which more explain the more variation for degrees of freedom. See, variation for degrees of freedom is nothing but mean squared. See, variation of explain more variation per degrees of freedom. Explain more variation by that one means mean squared regression. See? Then the Q6, then you have a respondent. 4 is the respondent. Yeah, if you know their research experience, how could you know that what's the chance of that particular person? See, I would say this is my with that research regression. I'm gonna get the research regression. Okay, we know that model now. Huh? What? This one. This one. See, CGP. Make sure you put the CGP. Okay? And I'm gonna make a function. See, function. See, make a function. So I'm gonna do this one for all four models. Okay, I did the for. I'm gonna do this one for research. The first one research. Sorry, the first one research. That is the second one. Make a function. Okay, research. Then make a function of this one for the with respect to second variable. And for the third variable, make a function with respect to that model. The fourth one, make a function. Okay. Now I'm going to go to the respondent. I can remember I go to the data. I'm going to go to the 40th person. And I pick the research. See, I call that one A. See, 40th person research. See, no, I'm going to put that into the research function. Research fund. Do you have a research fund? Research. Yeah. See? Research fund. Research fund A. Yes. See? There's a chance of 63%, 64, 66. Then I do the with respect to research. I'm filling this out here. Okay. Here. 40th person. 40th person. See? It's called the DAT for research. See? That one. Okay. Or straight you go to the research function and put 40 inside. See? Go to the DAT and pick that one rather than going this way. Or see, I'm still here. See, I'm trying to find the research. What is the chance of this person get admitted to the college? Here, I'm here. Then I can check this one, this one, this one. Okay. So I can get this done either by go to that person research experience, whether yes or no, I pick it up. Or that you straight go and put it here like that. See? Okay. Same answer. See? Or you go to the data and the 40th person, see, you keep it open. 40th person, whole thing you're going to take into account. See, whole line. See, whole line. It's all the information. See, that I call the that 40. See, 40th person, all the information. See, from that one, you say, I go to the DAT 40 and I like to pick research from that guy. See, if that's the case, see, another way to get it this way. Or simply you're going to predict the research regression because it's a part of that. See, 40th person is already included. See, and predict. See, predict, and you don't know prediction has been given for whole list, everybody's prediction. See, I need the 40th person prediction. See, I narrow down that. See, it's the same thing. See, predict research regression. I think this is the same thing. Research predict. The 40th person, I think this is the same thing. Or you go to the predict and say research regression and the 40th person. See, research regression, they both put together. See, 40th person predicted value, estimated value of chance of admit. See, research regression, predicted value. Whose predicted value? 40th person, 40th respondent. Same thing. See, another way to do that. See? So in a similar fashion, you can do for all of them. See, then I can use everything I put together. See, 40th person what? CGP. Same value. Yeah. That value. And total this value. Okay. You pretty similar. Okay. And you do the same thing for the 56th person. You do the same thing for the 93rd person. Then you're gonna ask, okay, you can do that one in similar fashion. From the base model that predict the outcome variable, question number 5, edit the following question. You can remember, you put their values back for the chance of admit with respect to GPA of the ith person. See? Just put it back. See? That's it. With the value that you would use to make the prediction with. See? Now this is the prediction part. Chance of admit, see, hat of the chance of admit equals negative 1.0755 plus this one. See, chance of admit hat, okay, hat. Extra credit would be that you go to the person, 100%, see, 100% error, see, value that's subscripted by I. Every value you put it back. Look at the chance of admit. I'm sorry, here. See, extra credit. I'm gonna go to the 100%. See, 100%. 100% and make a function. The 100%. See, create 100 and go to the CGP. If you put to that their model, see, the value 0.78 this much. I go to the GPA. See, CGPA is the best model. From the best model, you're gonna calculate the 100% chance of admit. See, so look at chance of admit for that in my model like that. Hat estimated value. Okay. 100%. At 100% GPA value. GPA function. You go to GPA function. Can you remember GPA function? You get the GPA function. GPA fund. See, we created GPA fund. GPA fund means you put the regression and value. If you give the value of that particular person's that chance of admit, sorry, GPA, it will calculate and give the estimated value. See? Estimated value. See? 0.78. See? So chance of admit, why we have 8.88. 100%, get 100. We're gonna check this one more time. Data 100% entry. I'm gonna check the 100% entry. Okay. I'm gonna ask them to give CGP. His GP 8.88. It's not right. Yeah, that's why I was going. Let me see what happened here. Okay, this is a real value. See, this is a real value. See, 8.88. Okay, this is the value that you're gonna plug in here. Okay, if you put that value to this GPA function, chance of admit is 0.78. That's what it says. And the chance of admit I'm going to calculate. See, see, I'm going to calculate this way. Look at this way. Should calculate this way. See, B not earlier was, see, now they don't work. Earlier it was working. That's the same thing. I'm going to say if this person GPA is 8.88, I'm going to plug in into this one, B naught and B1, we know. Okay, 0.78 to 6. See, this person GPA 8.88. This person, the chance of admit 0.79. 0.79. Then what are you going to do? Then you're going to find their difference. How do you find the difference? See? This person, see? That's the same thing, see? Look at 78.30. Okay. That's the same thing. If I do like this, I get the 78.30. See? Round to this one. That's the same thing. I'm here doing this the same thing. Okay, I would say, see, I'm doing the same thing. Okay, estimated value for the chance of admit for the 100% based on his GPA. Let's say, oh, this one. Then what I'm gonna do, see, predicted R, using R, I can get the predicted value, see, for the 100%, see, GPA function, data, CGPA, see, data, see, that's the same thing, but what I'm trying to do, I got the same thing. I gave a name for that one, R predicted value. I'm going to reproduce it for the 100%, 78.30, we know that one. I'm going to predict the GPA equation, see, from that one. See, and then look it into this value. See, all of people's value. I'm going to narrow down to this one to the 100% one. Then I get that one, see. That's the same value that I'm doing here. Oh, okay. Oh, this way. Another way to find that one. See, the same thing. Okay, the same thing. Then I'm gonna go to the my true value, observed value of the go to the thing. Data 100% chance of admit. What's the true value? See, true value. Look at the true value. 0.79. Observed value 0.78. Then what's the difference between those two? Called the residual. See, residual. Residual. See, see, you can find the residual by chance. This one, see, this minus that. Or go to the 100% one, then go to the predicted 100, then the residual. Same thing, 0.006. Or go to the resid. See, resid will give you all the people one. I don't need all the people. I want to narrow down to my 100%. See, that's why we put the bracket, okay? And then see, 0.006. Then you're going to put it back into the form. See? Put it back into the form. See? Chance of admit is 0.7. This is B naught. This is Y. Okay, this is a true value. You know true value, 0.79. This is B naught from the data. This is B1 from the data. This is the true value of that your CGP. This is the true value of chance of admit. Plus is the error. See? Same as 0.79. See? That's how we expect you to show every term. This. In order to find the error, you find the chance of admit for that 100% minus chance of observed or estimated chance of admit with respect to the GPA model. You saw the gap is 0.006. Okay, anyhow, that I'm gonna go ahead and then stop over here because I have to go to the other class. And then, do you guys have any question? If not, I'm gonna go ahead and stop over here, continue the same discussion, and then plus that we can go through the quiz too, and then we can add something that if you would like to discuss tomorrow too, that we don't have to narrow down our discussion like I like to do the way that I did in the beginning and show you so many things that you can see ahead of the time. They were not being tested, but for your knowledge. So these are you have to do anyhow down the road. Those kind of a thing. If you like to learn something, I can add to do rather than restrict our discussion and then broaden our knowledge in every direction. And then mainly that we can go through the quiz as well. Okay. Tomorrow, the same time and 5:30 to 6:30, 1 hour, 2 hours we can do. Okay, tomorrow, okay, because tomorrow I don't have a class. So the other class, if you don't have any question, then I'm gonna let you go. You guys have a good night. Stay safe and be well, and see you guys tomorrow. Take care. Okay. Thank you very much. Okay, and have a good night. Take care. Okay. Mhm. Okay. Thank you. Okay. Have a good night. Take care. Thank you very much. Okay. Good.